Hello. We're still waiting for our speaker. So, yeah. Yeah, because I know exactly what this is about. Um, so let's give it 5 more minutes, but obviously I'm going to end on time. So you just have less time to talk, unfortunately. Otherwise, I do have to apologize. We might have to cut it. Just to reiterate, our speaker is MIA at the moment. This should be the high performance networking in Python. And let's give him till 35. If he's not here, then we might have to cut it. All right, that's time up. I'm sorry to announce that we're cutting this talk because our speaker isn't here. Hopefully this is enough time for you to go to other talks that you want to go to. I don't want to delay any longer. What? No talk.
It's not going to be rescheduled. It's not going to be rescheduled.
I don't know. I'll talk to the organizers. Oh, no worries. Oh, here he is. Here he is. All right. Good job. Made it.
In the app it says 11:15. In the EuroPython app. Yes, it does. Check it out.
No. That's
I need HDMI. Do you have HDMI?
There's an HDMI thing down there.
Can you copy this?
Yeah. So I think that's HDMI to VGA.
I don't have VGA.
Okay. What can your laptop do?
Oh,
There is no HDMI.
okay.
But if that's a laptop,
that should work. I can write
should
it on a
work.
flash card.
mini display port.
Is it mini display?
Yes, it is.
Okay. That's fine.
I think we're good. Yeah, I think we're good.
Cool.
Thank you for doing the dash.
Okay. Does it work? Yeah. Yeah, sorry about that. In the official EuroPython app, it says 11:15, and then I saw a Hynek tweet that I'm missing out from my own talk, and I was like, oh my god, what's going on? Yeah, anyways, about me. So I'm from Toronto, Canada. My name is Yuri Selovanov. I'm co-founder of Magic Stack. Check out our website. It's magic.io. I'm an avid Python user since 2008. I think the first Python version I started to use actually was Python 2, but then in a month I switched to Python 3. I used it since Alpha 2 or something and never looked back. So use Python 3. I'm C Python core developer since 2013, but I believe I actually started to do things even before that. You might know me from PEP 362, which I co-authored with Larry Hastings and Brett Cannon. It's Inspect Signature API. Then I've created PEP 492. That's async await that we have in Python 3.5. And I'm also helping Guido and Victor Steiner to maintain async IO. I also created UV loop. More on that later. Structure of the talks. I actually wanted to tell you so much about how to write high performance code in Python and in async, with async IO in particular, but unfortunately I had to cut my slides, like I don't know, 50% of my slides had to go. So we'll briefly start with an overview of async await. Then we'll quickly cover async IO and UV loop. Then we'll answer or try to answer a question how you should write your protocols, how you should implement them using sockets or protocols, or maybe you should use streams. Then I'll present you with something new. It's a new high performance driver that I open sourced like 2 hours ago. And then we'll recap. I have to say that there will be no funny cat slides just because performance is hard. So only sad and depressed cats from now on. So let's start. There should be just one obvious way to do it, right? So we have 5 different ways to do coroutines in Python. First one is to do callbacks and deferreds. I think Twisted actually started and originated this approach. One of the first major frameworks, at least, that used that and kind of validated that it is possible. Then we have stackless Python and greenlets. And I'm pretty sure everybody heard about eventlet and G-event. That's a good example of frameworks that use them. In short, programs in G-event look like normal programs. They kind of look like you are using threads, but instead it's just one program, one thread, and every point of your code can actually suspend and then resume. It's a lot of dark magic, and as Guido said, it will never be merged in CPython. So those guys are kind of on their own. Then we have yield. And it was possible to use generators as coroutines in Python since I believe Python 2.5 or something. And Twisted has a decorator called inline callbacks so that you can kind of implement modern looking code using coroutines in Twisted, and you could do this for years. Then in Python 3.3 yield from was introduced, and async IO benefits from it. That's how most of the async IO code is written, using yield from. And then in Python 3.5 we have async await. That's the new way. And why do I think that async await is the answer? Well, first of all, it's a dedicated syntax for coroutines. It's concise and readable. It's easy to actually glance over a large chunk of code and see what's actually going on. You will never confuse coroutines and generators. There is now a new built-in type for coroutines. It's actually the first time in Python history that we have a new dedicated built-in type just for coroutines. We also have new concepts, async for and async with, and I believe this is something rather unique to Python. When we added async and await, a lot of people actually told us, well, you copied it from C#. Well, yes, we copied it from the C#, but we also introduced new things, and I believe this kind, async for and async with, are kind of unique. Like I haven't seen any other imperative language that has this construct. Async await is also a generic concept. A lot of people think that async await can only work with async IO. That's not true, actually. Async IO uses async await, but you can build entirely new framework and use them on your own. That's, for instance, what David Beasley did with his framework called Curio. He uses async await in a completely different way from how async await is used in async IO. And also, async await it's fast. If you write something like a Fibonacci calculator, you will see that it will run just twice slower. And that is fine, actually, because even in big async IO programs, you don't have as much async await calls as you have normal function calls. You cannot even compare. It's like 100 times more. So use async await as much as possible. It won't hurt your performance. You won't see any drawbacks. So coroutines are subtype of generators, but not in the classical Pythonic sense. In Python, they share the same C struct layout. They share like 99% of the implementation, but coroutine is not an instance of a generator, actually. And you can see this. The sharing of the machinery, if you for example disassemble a coroutine, you will see that it still uses yield from opcode. Then we have types coroutine. Originally we introduced it to make old style yield from coroutines from async IO compatible with new coroutines that uses async await syntax. Because you cannot just await on things. You can only await on awaitable objects. So you cannot await on number one, and you cannot await on a generator. But if you wrap a generator in with types coroutine decorator, you can await on it, actually. And again, David Beasley uses this kind of creatively in Curio. If you are interested in async await, I definitely recommend you to take a look at how async IO is implemented and how Curio is implemented, just to compare it to different approaches. And then we have a bunch of protocols for async iterators and async context managers. Let's move on. Let's talk about async IO, libUV, Cython, and UVLoop. So async IO is developed by Guido himself originally. I think a lot of it is inspired by Twisted. And it's actually good, because Twisted existed for, I don't know, 20 years or something, and they validated that this concept of asynchronous programming in Python actually works. So I think we copied quite a lot from Twisted, and Twisted actually plans to use async IO at some point. When they fully migrate to Python 3, they will just use async IO event loop. A lot of people call async IO a framework. Well, it's not a framework. I would call it a toolbox, actually. It doesn't implement HTTP, for instance, or any other high-level protocols. It just provides the machinery and APIs for you to develop this kind of stuff. If you want HTTP, you probably would use AIO HTTP for that. If you want a Memcache driver, you go and Google it. And it's also part of the standard library, which is both good and bad. Why is it bad? Python has slow release cadence. We see new Python major releases every year and a half, and bug fix releases usually are half a year apart. And I would say that for async I/O, sometimes it's not enough. Sometimes we discover bugs and we want to fix them as soon as possible, but we have to stick with the Python release cycle. But it's also good because you kind of know that async I/O will stay with us for a while. It will be supported by someone always because it's a part of the standard library. And also, Python has a huge network of build bots with different architectures and different operating systems. And it's quite important, actually, to test something as convoluted and as hard as I/O on different platforms. So it's good. Async I/O is quite stable right now and will be even more stable pretty soon. So what's inside async I/O? So we have standardized and pluggable event loop. Actually, async I/O from the beginning was envisioned in a way that you can swap the event loop implementation with something different. It defines protocols and transports. That's one way to actually marry callback style programming and async await is to actually develop protocols using low-level primitives such as protocols. It also has factories for servers and connections and streams, and this is also quite important because if you implement a server, let's say using blocking sockets, you implement it once and then you start to implement it a second time, you will see that you have lots and lots of boilerplate code that kind of looks the same every time. So async I/O takes care of that and factors out all of this implementation and convenient helpers for creating servers and creating connections. It also defines features and tasks. Task is something that actually runs the coroutine, that pushes the value into coroutines, that suspends them and resumes them. In a framework-independent way, it's called coroutine runner, actually. And features allow you to interface with callbacks. That's how you actually introduce async await into something that uses callbacks. It also has interfaces for creating and communicating with subprocesses asynchronously. It has queues, and by the way, queue is a very useful class. You should definitely use it. It's exceptionally hard to create an asynchronous queue that supports cancellation stuff, all the stuff like that without bugs. Like we still fixed a lot of queue bugs in 3.5.2. So queues are useful for things like connection pools, for instance. Definitely check it out. And we also have logs, events, semaphores, everything like that. Everything that nobody knows how to use, actually. And as Lukas Lange said on his talk on PyCon US a couple of months ago, if you love deadlocks, you can still have them in async I/O. So event loop is the foundation. It's the engine that actually execute async I/O code. It also provides factories for tasks and futures. It's also an I/O multiplexer. That's the engine that actually reads the data and pushes the data to the wire. It provides APIs for low-level APIs for scheduling callbacks, for scheduling timed events, for working with subprocesses and handling Unix signals. And the best part about it is that you can replace it. So that's what we kind of did with UVLoop. UVLoop is 99.9% compatible with async I/O. I'm not aware of any incompatibilities, but maybe there are some. As far as I know, you can drop in UVLoop in pretty much any program and it will just work. It's written in Python, and by the way, Python is just amazing. It's unfortunate that It's not as widespread, and I think it's kind of underappreciated what you can do in Cython. Essentially, it's a superset of Python language. You can use you can strictly type it, and it will compile to C, and you will have C speed. You can easily achieve it with a syntax closer to Python. So definitely check out Python and Cython and try to use it. UVLoop uses libuv. Libuv is something that keeps Node.js running, actually. Node.js uses libuv as its event loop. And it's actually a good thing because Node.js is super widespread and it's very, very well tested. So libuv is stable and it's fast. It also provides fast tasks and futures. So even your async await code runs faster on UVLoop by about 30%. And it's also thanks to libuv and a few hacks. It's super it has super fast I/O. So how fast is UVLoop? Well, compared to async I/O, it's 2 to 4 times faster on simple benchmarks like Echo Server. Again, nobody probably deploys Echo servers in real life. So as soon as you add more and more Python code, of course it will become slower. But again, even in real applications, I've seen reports that that UVLoop runs code about 30% faster. And also the latency distribution is much better with UVLoop. So it's faster than async I/O. What about other platforms and frameworks? For instance, the same Echo server written in Python that uses which uses UVLoop is 2 times faster than Node.js, and it's kind of interesting because Node.js is itself written mostly in V8. That's the JavaScript implementation. It uses libuv, which is written in C, and there is a thin layer of JavaScript on top of it. So still, UVLoop that uses the same libuv is 2 times faster for the same, almost the same amount of code. It is as fast as Go, run with Go max prox set to 1. That essentially means that Go cannot parallelize on multiple CPU the load. But still, it's quite an impressive result because Go is like a fully compiled language, and it also has, I think, a bit more efficient implementation of I/O than libuv, just because libuv is trying to be generic. It supports Windows, it supports Unix, and Golang supports it too, but in slightly different way. Anyways, and of course it's much faster than Twisted and Tornado, just because it uses a lot of it is in C, like most of UVLoop is in C. So initially, my idea for this talk was to end with this slide, just use UVLoop. Thank you for your time, questions. But unfortunately, it's not that easy. So, part 3. Let's talk about sockets, streams, and protocols. That's basically one obvious way to do it, episode 2. So what should you choose? Should you use coroutines like sock send all, sock receive, sock connect, or should you use high-level streaming API? Or maybe you should use low-level protocols and transfers. Here is an Echo server implemented with loop sock methods, and if you look at it closely, you will see that if you kind of drop async and await keywords, it looks like a normal blocking code that uses the socket module. It is kind of convenient when you have lots and lots of code and old-style code, blocking code. You can kind of easily convert it to async and await. Here are streams. Here is the streams version of the Echo server. It's quite high level, as you see. You don't work with sockets anymore. You have reader and writer. And here is a low level implementation of Echo server using protocols. So essentially, protocol is something that the event loop just pushes the data in, and protocol has a transfer to push the data back to the client, to the server. So the key method here is data received. That's like the main method. The event loop pushes the data to the data received, then protocol can process the data and then call transferred.write to actually send the process data or send a response back to the caller. For Echo Server, it's quite a simple implementation, but you can imagine it gets pretty hairy for more complex protocols. So downsides. When you use low-level loop.suck methods, loop cannot buffer for you, so you are responsible to implement the buffering on top. And you also have no flow control, which without buffers doesn't make any sense. You don't need flow control, but when you start implement the buffers, you won't have it. And it's quite a tricky thing to implement correctly. And another thing why you shouldn't use it is just because the event loop has no idea what are you doing right now. Let's say you are reading some data. Okay, event loop will add your file descriptor to a selector, which can be EPOL or KQ on Unix, and essentially wait for an event. And when it receives this event, it will try to read the data, push the data back to you, but it will also remove the file descriptor from the selector. That's an extra system call. Because it doesn't know, will you continue reading the data, or will you write the data now, or will you just stop, or will you close the connection? So it cannot predict what's going on. When you use streams, and streams are, by the way, are using protocols, event loop just knows, because you have an intent. Just keep sending me data to my data received or to my stream, and when I don't need this data, I will close the connection myself. So event loop can actually optimize for that. And flow control is kind of important. I like this picture because it illustrates that sometimes you kind of have to push back on something slow or something that you don't want to use right now. So which API you should use? You should use loop.suck methods when you are quickly prototyping something, or when you are porting some existing code. But I would highly recommend you to actually stick to streams. Even for porting code, just rewrite it in streams, because streams are much easier to use. You can just say, give me exactly this amount of data, or you can tell streams, read until you see /n or something like that, and it will do it. It also implements a buffer, read and write buffers quite efficiently, and you can use async await to program the entire protocols with streams. And use protocols and transports for performance. Actually, if you want exceptional performance, you have to go low level. So for this talk, let's focus on protocols and transports. And again, it's kind of important. For your application code, you should always use async await. Never even touch, never think about transports and protocols. This stuff is just for drivers. Drivers for PostgreSQL, for Memcache, for Redis, for any kind of this kind of code. High-level code should never think about protocols. Always use async await, it will be enough. So let's focus on protocols. So as we mentioned before, loop pushes data to protocols. Protocols send data back using transports. And protocols can implement specialized read and write buffers. They can also do flow control. They can hint the event loop through the transport.resume and pause read methods. And you have full control over how I/O is performed. You call transport.write. You can pause or resume data consumption. So you have tools to control the I/O. So how to use protocol and transports? There are basically two strategies. The first one is you implement your own abstractions, your own buffering, and your own stream abstractions. And a good example of that is AIO HTTP. That's what they do. They have buffers and streams specifically designed to handle and parse HTTP protocol, and then they just use async await. It's a fine approach. It will be slower than using callbacks and accelerating everything in C, but it's quite good. Still quite good. So the second strategy is to actually implement the whole protocol parsing in callbacks, and then create create a facade that allows you to use async and await. And the main key reason why this is a better, might be a better strategy and why this can offer better performance is because you can just drop Python completely. You can go low level, you can use Cython, you can use C. So part 4, async PG. This is something that I just open sourced a couple of hours ago. This is right now the fastest PostgreSQL driver for async IO and for Python actually. It's 2 times faster than PsychoPG. It completely re-implements the protocol from ground up. It doesn't use libpq, that's the de facto library for working with PostgreSQL. So we just implemented it completely from scratch. It uses Postgres binary data format. And by the way, when you are implementing protocol and you have a choice, use text or binary, always choose binary. It's easier to read binary, it's usually just less data because the encoding is more efficient, and you can process it much faster. You can, because, well, how binary format works, usually you have a length field that tells you how much data follows this frame, and then you have another one, so you can read frames much faster, you can decode types much faster. So always choose binary. And also, not all Postgres types can be encoded in text and actually decoded from text. So composite types, for instance. If you have a recursive composite type, it's just not possible to decode it in PsychoPG. So what we did for async PG, we actually forgot about DB API completely. There is no DB API for async await, but for instance, what AIOPG does, they kind of sprinkle async and await on top of existing DB API. So our idea was let's build a driver that just is tailored for Postgres and uses Postgres features. And we also support all built-in Postgres types there is, basically. So Postgres loves prepared statements because it doesn't need to actually parse the same query over and over again. When you prepare a statement, it has basically some structure on the server with a plan, with a parsed query, and Postgres already knows how to accept your arguments and do this kind of stuff. So we use prepared statements every time, even when you don't explicitly create them. We have an LRU cache of prepared statements, and we do that transparently for you. We also dynamically build pipelines for efficiently encoding and decoding data. So the pipeline is essentially an array of pointers to C functions that can process the stream like with enormous speed. So and it actually shows. This chart compares different Postgres drivers for different languages. The fastest one is async PG. It manages to push almost 900,000 queries to the server. The second one is AIOPG. That's another driver that uses libpq, which is also written in C. But unfortunately, PsychoPG doesn't provide an efficient async interface, so it's slower. And also, async PG, AIOPG and PsychoPG, they use text data encoding, so it always will be slower. Then you will see 2 Go implementations, and then you will see Node.js drivers, which are just 10 times slower. The funny part about this one is that Node.js PGs is actually pure JavaScript implementation of the driver, and PG native is using libpq. So somehow a lot of JavaScript is faster than C. I have no idea how. The funny thing about this performance is that there is another library. It's not a part of this chart because it's kind of slow. It's called PyPostgreSQL. Nobody knows about it. We used it for several years, and then we just created async PG. Anyways, it's a pure Python implementation, and it's as fast as pure JavaScript implementation. So everybody is saying that Python is slower than JavaScript. You shouldn't use it, but we kind of saw that it's possible to write a pure Python code that as fast as Node.js code. So maybe Python isn't that slow. Async PG architecture, it's basically implemented in the meat of it is implemented in core protocol. Core protocol is something written in Cython. It uses callbacks to process the protocol. Then we have a protocol class that just wraps core protocol, and insert some future objects into it so that you can use async await. And the rest of async PG is just pure Python implementation that just implements the high-level API. So how would you parse Postgres protocol? Naive approach would be just to use Python bytes and memory views, but unfortunately, doing so will cause a lot of Python objects to be created, and you will actually see how long you spend on memory allocation. So the solution is to use Cython and go to the C types, and just don't even touch Python bytes and memory views. So this is a preview of read buffer. It's a bit bigger than this. It's API, but you can see the first method is the most important. Feed data. That's what protocol data received actually calls. Protocol data received has just two lines in it. The first one pushes the data to read buffer, and the second one calls a function that just reads from the buffer. And this buffer is kind of tailored for Postgres protocol. It has low-level read int 32, int 16, and the second most important call here is try read bytes. Try read bytes either returns you a low-level C data type, or it returns you a null pointer. And if it returns a null pointer, then you actually call read, which returns you a Python object, which is much slower. But most of the time, 99% of the time, try read bytes succeeds, and we can avoid creating any Python objects. So again, high-level logic of async PG is built in pure Python. That is how you can actually use it. You can see it's a pretty high-level API. We prepare a statement, we enter a transaction with async with, and we iterate over a scrollable cursor. Part 5, let's recap. So don't be afraid of protocols. Use them to implement really high-performance drivers, and use Cython for low-level code. It's really much easier to code in Cython than in C. You can quickly refactor your code completely, change everything, and it will just work. Async await should always be used in your application code. Don't think about protocols and transport. Use only high-level code. And again, once you have fast database drivers, memcache drivers, stuff like that, and you use UV loop, you will see your application being much faster. Loop create future was introduced in Python 3.5.2. Actually, that's a new feature. With this, if you use loop create future, UV loop can actually inject fast future implementation into your code, because UV loop implements its own version of the future, and it's about 30% faster than async.io future. Always use binary protocols. Never even try to parse text protocols. It doesn't make any sense. If you can do binary, go binary. Always profile your code. It's actually funny because when async PG actually started to work, I benchmarked it against AIO PG, and it was 2 times slower. And I didn't understand why, because it should be faster. Like, there is no way it can be slower. So I spent about 30 hours without sleep optimizing async PG and made it 4 times faster. The important lesson from this is that if that first run showed that async PG was like 30% faster than AIO PG, maybe I wouldn't spend so much time trying to optimize it. So always profile, always analyze, and try to push it forward. And by the way, Cython code can be profiled with Volgrind, and you can visualize results in Kcache grind. It's a very useful tool. Check it out. And Cython has a useful flag. It's called -a. It generates HTML representation of your source file, and each line is highlighted. It's either blank or it's a shade of yellow, and the most yellow lines use more Python C API, and it is slow. So basically, you have a quick way of analyzing your Cython code. Its speed. So definitely check out that option. Always try to do zero copy. Try to avoid working with bytes, memory views, all this kind of stuff. Go low level with Cython, and don't copy Python objects. Never. And one of the last advices actually is to Implement an efficient buffer to write data. For instance, for async PG, what we do for writing messages, we have a write buffer that just pre-allocates a portion of memory, and then we compose messages in with high-level API, and we don't touch that memory at all. And when the message is ready, we just send it. So we have high-level API of creating the message, but we don't allocate any memory while we are doing so. So when you have this this control, you should definitely set TCP no delay flag. We probably will set it by default in async IO in Python 3.6. Right now it's not set. You should do it because it will speed up transfer.write method. Basically, with this flag set on the socket doesn't wait until it receives a TCP ARC message. It just sends the data as soon as you do it. But if you don't have control over how frequently you are calling transfer.write, you can basically use TCP cork. What you do, you cork the channel, then you do multiple writes to it, then you uncork it, and it just sends all of your data in as few TCP packets as possible. And the last slide is timeouts. Always implement timeouts as part of your API. Don't ask your users to use async IO wait for, because wait for is slow. It wraps the coroutine into a task, and that comes with a huge penalty. Your code will become 30% slower if you use wait for. So design timeouts as part of your API. At the lower level, implement timeouts with loop.call later method, and it will just work. That's it. Thank you.
Yeah, so I think we have time for maybe one or two questions. Please use the mic.
Hi, thank you for the presentation. I want to ask you about using async IO and UV, your event loop, not for high performance, but for high concurrency. Do you have would you use it for high concurrency? I have a scenario with hundreds of thousands of concurrent connections, but
yes, UV loop is even better for that because it uses less memory than async IO.
Don't hear you.
UV loop is much better for a highly concurrent application that handles like hundreds of thousands of connections, simply because it uses less memory. Again, it's faster. We tested UV loop with 100,000 connections, and it handles it. It's pretty okay.
Thank you.
Unfortunately, this is all the time we have. Thank you.
Thank you.
Let's say 10 minutes.
10 minutes, okay.
So if you could give me
I'll subtract, I guess. So
give me the 10-minute warning at 11:45.
okay, sounds good. Thanks.
And then that gives me, well, it's lunch afterwards, isn't it?
No, we have one more session.
Make it 11:45 then, because you need 5 minutes for people to shuffle.
Got it. Thanks.
Hello. Where is you? Where is you? There you are. Okay. Apply that. Keep this configuration. Right. Okay. Ah, damn. It's F11 for full screen, isn't it? Oh, right.
Is there a particular way you'd like to be introduced?
Yeah. Great. Let me just check. Yep. Okay.
Thanks. Hi everyone, thanks for coming. This is Cloud ABI talk. Just make sure you're the right ones. Yeah, so we have Alex Wormer speaking to us about the securities on Linux.
Greetings, everyone. Thank you for coming to this briefing on the inquiry into the Sol 3 defeat 20 cycles ago. Contents of this briefing are classified Duchess Royal Bud Line. Anybody who does not have that classification must leave the room now. Okay, with the formalities over, we can begin. My name is Alex Wilmer. My mother was Susan Wilmer. She was chief of docking during the Sol 3 harvest 20 cycles ago. It was her that allowed that fateful ship to dock, scout ship TLV 3495, the one that we'd presumed destroyed aeons ago. This was the ship that was carrying 2 human cable repair engineers. Those cable repair engineers were carrying their Jolly Roger superweapon. That led to the destruction of the entire fleet and the loss of the Sol 3 harvest, along with nearly 1 billion mines. I've been part of the team for the last 15 cycles investigating the reasons for this defeat. There were many contributing factors. Our synchronization signal impinged on human communication bands. They were able to detect this and from this calculate the time of harvest. This resulted in their human leaders surviving the initial harvest attack. There are numerous smaller incidents, such as trainee GX firing on a human welcome wagon. We've seen such attempts to communicate before. They've of course never been successful. But in this case, critical seconds were lost in confusing the humans, and they were able to escape the initial fireball. Another example I would like to highlight, following the initial counterattack by the humans, which was of course futile. Their kinetic weapons, their missiles, could not penetrate our energy-based shields. But in one case, a downed ship did lead to the capture of the pilot. The pilot was taken to the human leaderships, where a pilot was tortured, interrogated, mind probed. During this, the pilot did reveal our negotiating position, our harvest tactics, and our general disposition. This resulted in counterattacks by the humans of a thermonuclear nature. Of course, this was still futile, but they were contributing factors. Finally, there was one more that I'd like to highlight. The captured craft was not challenged. was not questioned when it approached our main harvest ship. This allowed it to gain access to the command carrier. This allowed the humans to gather intel on our initial invasion plans. All of these pale in significance to the principal reason for the Sol 3 defeat: capture of the scout ship. From this capture, the humans learned of our existence, they learned of our biology, they learned of our technology. Critically, they learned of our Unix operating system. From our technology, the humans went on to develop various things. Human code words include Roswell, Area 51, Unix, Bell Labs, ARPANET, AOL, email. All of these are pale imitations to our consensus net, of course, but they gave the humans a critical foothold into our protocols and systems that allowed them to upload a virus to reclamation pump 369282. That replication pump then communicated on ConsensusNet, spread, sent commands fleet-wide, resulting in the disabling of all protection fields. From this, the humans were then able to use one of their primitive thermonuclear devices, destroying our carrier ship. Our thoughts, of course, go to all the families of those aboard. So for the past 15 years, we have been carrying out the investigation. There are numerous lessons that have been made in procedure and command decisions. This briefing will concentrate on some of the technological implications. We find that the root cause analysis, PumpMon, running on that pump, was vulnerable to the human's attack. That is how they got their foothold. That is how they were able to instruct all defense fields to switch off. Without that, their attack would have been useless. The problem with PumpMon was not a simple buffer overflow or stack smashing attack. The problem was more architectural. PumpMon had numerous capabilities that it did not need in order to fill the role of monitoring that pump. It could read global files. It could monitor processes. It could create network sockets to other places on ConsensusNet. All of these were unnecessary, and all of these were exploited by the human Trojan. The table you see is a quote from the report. Please refer to that if you need the full details. So the architectural flaws of Unix boil down to discretionary access control. That is, access control is not enforced by default. There are things that are open that do not need authenticated access. This means that programs on Unix systems start with excessive capabilities. And once compromised, programs can acquire further capabilities simply by opening them. There are global resources and global states throughout the Unix system. This obstructs running programs securely. It obstructs writing testable programs because tests have to try and inject these normally global resources inside a restricted test environment. It obstructs writing reusable programs because these programs assume a full Unix operating system, and it is very difficult to audit them to say what do they actually use. System administration just does not work at harvest fleet scale. Beyond 1 million nodes, we just do not know what these systems are doing. Our team would like to propose a human technology that has actually been adapted from their reverse engineered version of our Unix. This human technology is called Cloud ABI. It is a relatively recent invention for the humans, approximately 2 years old. Under Cloud ABI, programs start with the ability only to spawn threads and to allocate memory. Unless they are provided with unless they are provided with access to external resources, they cannot access them. They cannot acquire further access to external resources. They can only do that through the capabilities provided to them when they are started. The implications of this are it is safe to run an unknown Cloud ABI binary if it is given no resources. The worst thing that it can do is allocate too much memory and burn through CPU. As a result of this, with explicit capabilities passed into the program at startup, it is much easier to audit these programs to say what they need. As a consequence, it is much easier to test these programs. This leads to better release engineering and could allow for higher level orchestration, the ability to migrate processes between hosts rather than virtual machines or containers. This could lead to more efficient resource use in fleets and certainly to more secure resource use. To give you a bit of background on this Cloud ABI technology, it was initially developed by a human called Ed Schouten. He is located in the European continent. It was initially for the human derivative of our Unix called FreeBSD. It is now available for multiple human operating systems and is compatible with our SenseNet and and original Unix. Some of you may be familiar with a human technology called Capsicum. Cloud ABI is derived from this Capsicum project. In Capsicum, processes initially gain access to global resources and can acquire further resources just like any other Unix process. But a Capsicum process can call a function called capenter, after which syscalls that allow it to acquire further resources are blocked. They return an error and/or result in the process being killed. This allows for more secure processes after they've left their initial startup phase. The problem with this Capsicum project is that integrating external library into a Capsicum process causes runtime errors, strange behaviors, Heisenbugs. Because a library buried deep in the call stack might try to open a file, might try to initialize a pseudo-random number generator from a device, and then fail and fall back to a less secure method such as the time of day or the current PID. The innovation that Cloud ABI takes is to make Capsicum default. It is always on. Cloud ABI processes cannot call open. They cannot see global resources such as process tables, file systems, or user databases unless explicitly given access. To give you an idea of what we remove, all of these APIs are unavailable to a Cloud ABI process. The first category is simple common sense. These are APIs that were not greatly designed in the first place, or they tend to result in buffer overflow bugs. There are thread-safe, buffer-safe alternatives already available for both Unix and Cloud ABI. The second category is basically the Unix file system. On a Unix operating system, a process can open or attempt to open any file by its path. This is impossible in Cloud ABI. There is no open function. There is no stat function. There is no get PID, there is no get UID. Next, we move on to mutable state functions. These are ones that tend to have an effect process-wide, regardless of whether a process is multi-threaded. These are removed because they make programs harder to reason about. Removing them simplifies the API, and there are thread-safe alternatives. Standard in, standard out, and standard error are also removed simply because they are a global resource that should be explicitly declared. argv is also removed. The method of passing in arguments to a Cloud ABI process is incompatible with argv, which relies on acquiring resources based on string values. This is disallowed. After removing these things, we add one simple concept. Unix file descriptors become capability tokens. These are the tokens by which a Cloud ABI process acquires all resources. All APIs in Cloud ABI that allow acquisition of new resources require an existing file descriptor to be passed in. A file descriptor might describe a directory, a file, a socket, or even the handle to control a sub-process. The second thing we add is a single application binary interface. This means that a Cloud ABI process, once compiled on any Unix system, native or human, will run on any other Unix system without recompilation. The ABI is available for the following human systems: FreeBSD, Arch Linux, Debian, Ubuntu. It is even available for their Mac OS. Support is in progress on the Linuxes, but with the next release of the humans FreeBSD, it will be a native feature. So, it's best at this point to illustrate with an example. We'll be taking a very simple noddy case of a Unix utility, ls. This takes the name or the path of a directory and prints out the names of the files and folders inside it. This is a very simple example, stripped down to illustrate our differences. You will note that the process is taking in a string and assigning it to the variable dir path. It is then passing this string down to the operating system, and the operating system is acquiring resources on behalf of the process. If we did not see the source code of this process, we do not know what it would be capable of. It might list the directory and send those results back to the humans for further analysis. It might encrypt the contents of the directory. It might delete them. It could do any number of things we don't know without fully auditing the source code. Using some of the features of Unix, we can come closer to a Cloud ABI design. In this one, the ls program does not take any string input. It receives only file descriptors. File descriptor 0 is the directory that we are trying to show the contents of. File descriptor 1 happens to be standard out. Given this model, if the program was unable to pass strings to the call to open and the call to list dir, we could say that this process was not able to do anything other than act on the resources we provided, namely read-only access to a single directory and everything below, and write-only access to a single file stream, namely standard out. The problem with this model is that it becomes very inflexible to pass in file descriptors in the exact sequence that they will be used by the program. So, the Cloud ABI system relies on a new mechanism called argdata. In argdata, there are a set of APIs to gather file descriptors according to a tree structure. Programs can acquire these by key name, as lists of file descriptors, or maps. In the example you see, we use a helper program called Cloud ABI Run to map a YAML file containing a description of the input to the program to the file descriptors that the program will receive. In this example, the Python executable is not a Unix executable, it is a Cloud ABI executable. Therefore, during the build of this Python executable, any reference to standard in, standard out, standard error, the C-level function open, the C-level function stat, the C-level function opendir would have resulted in compile time errors. As a result, we can safely say that this execution of this Python script cannot do anything except read the contents of a single directory and write the output to a single file descriptor. This makes this process safe to execute without trusting its source. We need only know that we have exposed the inputs we provide to that program. The inputs are explicit, not implicit. A further example, it should be mentioned at this point that this example is, at the moment, hypothetical. The Python port to Cloud ABI is in progress. It cannot currently do this. Other programs written in other C programs are fully ported, and there is a Cloud ABI ports set of packages available. To give you a further example of illustrating what might be possible, we show here an example configuration for a web server. The web server binary itself would not have its own configuration file. It could not read that file unless provided, and that file would contain strings referring to paths which the web server would not be able to open. So in this example, we combine arguments and configuration into a single file, and this file is provided to the Cloud ABI Run helper in order to acquire resources on behalf of the web server. Were this web server compromised, it could not start listening on new ports. It could not open a network connection to send the contents of any acquired data out to the world. All it could do is serve network traffic on the socket that we have provided. So at this moment, we ask, what can we do in the future with this Cloud ABI system? We might imagine a future where software appliances can safely run customer-provided plugins or third-party plugins without exposing the internals of their system or the entire operating system. These plugins would be provided with a limited set of file descriptors and would therefore be constrained in what they could do to affect the outside world. We might use this to isolate vulnerable systems such as PumpMon, or transcoding libraries for security cameras from fleet-wide security systems. By this means, we could avoid problems in error-prone libraries such as the human library ImageMagick, or the various video encoding libraries that have extremely complex input requirements and, as a result, tend to have many vulnerabilities found. We might imagine the ability to use Cloud ABI in order to implement the human system Amazon EC2 without the overhead of virtual machines or containers. Similarly, we might imagine the human system Google App Engine with the ability to submit programs written in any language, C, C++, Rust, assembly language. In theory, these would be safe languages to implement programs in and allow them to be uploaded to a third-party cloud service without virtualization. This would allow us to compose applications, not containers. I shall now show you a brief demo of what has been achieved with the human language Python and the Cloud ABI system. Of course, it would help if I showed this on the right screen. In order to run a Cloud ABI program on this system, we can use the Cloud ABI run helper. The Python binary you see has been compiled against the Cloud ABI system headers and version of libc. The Python binary itself cannot accept standard input or write to standard output. So the file that we are providing is going to the Cloud ABI run program, which is a Unix program. It is opening resources on behalf of the Python binary. The Python binary is then receiving file descriptors. Whoops. The demo gods. I don't know. So the contents of that YAML file look like this. At the moment, the Python binary is a work in progress. This is the first thing that got working with it. We have transliterated the native Unix Python arguments into YAML keys, and the command is given verbatim. We are also able to execute system calls. In this case, the Python script, the Python binary are burning CPU and then printing the result out to standard error. As a result of Cloud ABI, though, this is the worst that this process can do. We can kill it and know that it has done no damage to the system as a whole, because it did not have access in order to do that damage. If we have a look at the contents of resource.yaml, we see that all it had access to was read-only access in order to import its standard library, write-only access to the standard error file descriptor, and the ability to execute a simple syscall. Work will continue on the Python port to the Cloud ABI system. There will be a sprint running at the human event EuroPython 2016 on Sunday. If you would like more information, please visit these addresses on the Human Network. Our usual network taps on their networks are in force. Thank you very much.
So we have some time for questions. Okay, let's start with you and then I go with you.
Hi, I'm Jernej. Thanks a lot for the talk.
Hail the Queen.
Okay, awesome. So I'm wondering, we have in the community like a lot of tools that attack the same problem. We have AppArmor, we have things like OpenBSD. And SA Linux from NSA, no backdoors, I promise. So why another system?
So the problem that we have found in our experience with AppArmor, SE Linux, such systems, is that the incentives with them tend to be wrong. It is not the creator of a piece of software that configures those systems. It is typically the distributors and the system administrators. So, as a result, the configuration of the protection system, such as AppArmor or SE Linux, tends not to be in sync with the requirements of the programs that are running. So all too often, administrators in the midst of battle on a fleet ship will typically just turn them off. More so with inexperienced administrators, but even seasoned veterans of multiple harvest campaigns have been known to switch these systems off when there is incoming fire.
Yes, okay. Another question, if I may? Okay. So is this thing production ready? What's the overhead? And what's the biggest app you are currently running with it?
The system is still in its early phases. It was conceived approximately 2 Earth orbits ago, around 2.5 cycles. Until the creator has been working on it quite a while and is an experienced developer as humans go. The Python part of this is most certainly not production ready. It would be tricky even to call it alpha. Unfortunately, the human responsible for its development, some inconsiderate human gave them a job. So there was not time to complete it before this briefing.
Hi, thanks for the talk. I'm curious about the support for binary libraries like BCBox. Are they planned to be added to the Cloud ABI support? And we have seen a pattern common followed by humans, and they tend to use Linux a lot and avoid FreeBSD. Are they security-focused tools? And we are also seeing a proliferation of a new tool called Docker, who is taking a different approach to security. It's the acceptance of Docker threatened the future of Cloud ABI. Are we investing time in Cloud ABI when we are going to face a different problem in the next harvest?
So I'm pleased to report that the next harvest fleet is on its way to Earth, and they will pay for their treachery. The human technology Docker provides similar benefits to Cloud ABI. It has slightly higher overhead and is restricted only to their Linux operating system. The Cloud ABI for Linux support is 90% complete. It lacks integration with their distributions at the moment. We are working to improve this. What was the other part of your question, please?
BusyBox support.
Oh. So there is a repository available of... Oh, get over there. There is a repository available of human-derived software called Cloud ABI Ports. Do something. There are over 100 packages in this. I do not believe that BusyBox is one of them. The Cloud ABI model is better suited to long-running daemon processes than to interactive use. It can become quite not unnatural. It can be quite cumbersome in order to provide all the file descriptors to Cloud ABI binaries in interactive use in a shell. So that is possibly a development. But if you wish to see if a package has been ported, I recommend visiting the Cloud ABI ports link that was included in your notes.
Any other questions? All right, thank you very much.
And just one more thing, breaking out of character. If anybody would like to buy a house in Birmingham, it's been on the market a while, it's a bargain. Thank you very much. Thank you. Hi. Right, that.
That was a lot of work. Staying in character.
Yeah, I didn't quite manage it.
You will.
Do we have HDMI?
No.
Okay. Do we have audio from the laptop? Can we have audio from the laptop?
Yeah, he's on break now.
He's on break, okay.
Unfortunately, I do not have the answer for that. Would you try just pointing? You want still want to give it a try?
I mean, if in the worst case, we'll do that.
Okay.
But
yeah,
it'd be better if we can do audio from the laptop.
Can we do audio from the laptop?
There should be a cable.
Cable.
He's asked me to check that. That's what he's doing. But yeah.
Can you hear me? Is this working?
Okay, I'm set up for the visuals.
Okay, wonderful.
Yeah, but the audio would be a good thing to have if possible.
Yeah, so we're thinking about, they were asking for audio. Yes, I can hear you. Wait, you're silent now. Yes. Yes. Wait. All I can hear is, are you listening to me? And then it goes silent. Yeah, I can hear you. Mode. Oh, okay. Yes. Okay. So they are. Oh, so we're looking to broadcast audio from the laptop. How do we do that? This is an HDMI. Oh, wait. This is an HDMI. So
Yeah, but it's okay. The videos
Oh no, it's only video.
that won't help with the audio, unfortunately.
Right. Sorry, I lost you there. Can you say again? Thank you. Hello? This is this is not working as well. So we're this is you. Am I?
Yes, that's the one. Yes. So, what's the answer about the audio situation?
I think it's coming down.
It's coming down. Okay.
Yeah. So
And will
because I can hear you.
will I have a microphone that I can wear?
I don't think so, but there is a remote one.
Okay. All right. It's just that I might.
For Q&A, however, it might be better if you use this one. So that I
Okay.
can get
All right. It's just that I might, step away from here for a moment. So. Hello. Hello. I've got time.
How much time would you like for Q&A?
Well,
If any?
I've got a nominal 45 minutes because then it's lunch, isn't it?
Yeah.
Yeah. So I will try and get through this material as fast as I can and leave time for some Q&A.
Well, I just mean in terms of getting a warning. Should I
Yeah.
give you?
Let me know 5 minutes, but it may be that I have to. Let me know 5 minutes before the Q&A starts.
Okay.
Yeah.
So in total, I'll probably be about 10 minutes before starting. I'll give you the 5-minute warning. So with 5 minutes
Yes,
Q&A.
that'll be fine. Yes. Yeah. So you'll be doing that if I start at 12. We'll do that at half past. You'll give me the 5 minutes.
12:40.
You'll give me the warning at 12:40.
Yeah. The 5-minute warning at 12:40.
Okay.
Okay. Would you like to be introduced, or you're welcome to introduce yourself?
I can introduce myself. I'll introduce myself. I'll open start my slide up. So here we are. That's it. But I'll use these for the most part.
Okay.
And
It might you might need to give him some time to react and turn this one on.
yes. Okay.
Just
Yes.
letting him
Yeah.
know.
Anyway, or I can shout. It's only a small room.
Okay.
Thank you very much. I'll quickly introduce myself. I'm Daniele Procida, that's me. My favorite portrait of me, as you can see, it says I am Python software. Yeah, thank you. I work at Devio, a Swiss Django company, and I'm a developer of Django CMS. I'm a core developer of the Django project and a member of the Django Software Foundation board. You can find me in the usual places online as EvilDMP on IRC and GitHub and Twitter, and there's my email address there, so feel free to contact me about anything. So, firstly, thank you. Thank you for inviting me to be here, for being here to listen to me speak. Thank you especially to the organizers and volunteers of this conference, because if you're enjoying yourself here, it's because of them. I know how much work it is to run a conference, and to run a conference of 1,500 or so people is a pretty big deal. Things will go wrong. If things go wrong, it's not because they didn't care or didn't think, it's just because stuff happens. So if you see any of the volunteers or organizers, just say to them personally, oh, thanks, by the way, I'm enjoying the conference, because I can tell you as somebody who has done this that actually it means a great deal. So thank you to those people who are making this, thank you to those people who are making this happen. And of course to the sponsors who make it happen, make it possible financially, the speakers who have put a lot of time in, and all the participants who have come here to get together. As I said, I work on Django CMS. We're sponsoring, so we are also very busy this week. We've got a Django CMS help desk on Thursday. We're doing a Docker workshop on Friday, and we're sponsoring. So I got all excited that this is a great marketing opportunity, and the best I came up with is Django CMS, we're around your neck. So I don't know, maybe Twitter will come alive with better. No, I'm going to go into the office and get lots of congratulations from the team when that makes a big splash on Twitter, because I think we're around your neck actually works really well as a marketing thing. So I want to talk about minds and machines and Python. I'll have a tiny amount of Python code in this, and it's not very impressive. This is Alan Turing, the great Alan Turing, in a rare photograph of him smiling. And in his paper, Computing Machinery and Intelligence in 1950, he turned the question of whether machines can think onto its head. In fact, he said, the question, can machines think, is too meaningless to deserve discussion. And instead of asking whether thought can occur inside a computer, he wanted us to consider whether a machine could, in principle, be indistinguishable from a human in those respects that allow us to say a human thinks or has intelligence. So he turned the question about machine intelligence upside down. And he was applying insights from the philosophy of mind that emerged in the early 20th century, which also moved the questions of mind and intelligence away from a concern with the metaphysics of thought and the intrinsic nature of consciousness towards questions like what constitutes an interaction with intelligence, or how do we recognize other minds? So in other words, he was very much in line with, or following the footsteps, if that's the right word, of thinkers like Gilbert Ryle or Ludwig Wittgenstein, who argued the search for mind was not a search into inner mysteries, but a matter of recognizing what was in front of us all along. So we could say that this represents a kind of fork in the study of artificial intelligence. And Turing's argument, in a way, freed researchers from having to clamber into these kind of opaque mysteries of what goes on inside of consciousness and thought, and instead concentrate on producing, for example, interactions that seem like encounters with intelligence. And that's been the dominant fork, if you like, in artificial intelligence since then. And its fruits are all around us, I mean, literally in our pocket. So you've got your phone, you can say, you know, do I need to carry an umbrella today? Or what's happening, what events are on in Bilbao this week. And the power of machines to recognize stuff, like languages, faces, text, or road traffic, or not if you're in a Tesla sometimes, and to respond appropriately, has suddenly taken me by surprise. And I think it's taken many people by surprise just how good machines have become at doing this. And by Turing's account, I really do think that we're living at the beginning of an age of machine intelligence. But what about that other fork, that lonelier furrow, which fewer people have worked on, and we hear less about, but people have been working there and have been trying to unpick these mysteries of thought itself. So Turing was a very intelligent thinker, but just because he dismissed something as too meaningless to deserve discussion doesn't necessarily mean that that is so. So here are two people who thought otherwise, who disagreed with Turing. Joseph Weizenbaum, in computer intelligence research, he was the author of ELIZA, the program ELIZA, which was his attempt to demonstrate in a concrete way what was unsatisfactory about Turing's analysis, or the philosopher John Searle. So in this talk, I want to go back to that fork, because I also think that Turing's analysis, however brilliant and powerful it was, is a bit flawed and inadequate. And I think that the incredible advances of the Siris and the chatbots and the self-driving cars, as far as we're actually concerned with intelligence, I think those represent a dead end. So those things, like Turing's approach, begin from the outside. They're not really, I think, concerned with the nature of intelligence itself, but with the challenge of creating an appearance of it. What does intelligence look like? What does it feel to be in the presence of intelligence? And in narrow, limited spheres, this appearance can be extremely successful. And the more successful the appearance, the more easily we fall into using the language of intelligence around that behavior, sometimes forgetting that, some people might actually find this contentious, but I think that we're dealing there with a simulacrum of intelligence. It's really, in the case of, say, Siri, or a Tesla car, is no closer to consciousness than a stone. And I think the more interesting question is the neglected one, that begins from the inside, that asks what lies at the heart of intelligence, how and where does consciousness arise? And as programmers, I think we have the concepts and tools to investigate this in useful and interesting ways. And I want to argue two things in this talk. Firstly, that programming concepts give us the most interesting insights are in fact the most basic programming concepts, and that we can find their counterparts in the work of artists, poets, and writers, and that this helps us understand. So for this, we'll turn to the concept of poesis, a Greek word. It's where the word poetry comes from, and it means to make or to produce. And it doesn't mean making or production in the sense of manufacture. Think of French or Italian verbs like faire or fare, which they mean at the same time make and do. Or think in English about the way we would say things like use making friends or making love. That's the kind of making perhaps that is involved in poesis. Poesis is not concerned with material or technical construction, but with rendering a transformation in the world, an act through which, or a process through which something new is brought forth. In poesis, something becomes another kind of thing altogether. A new thing emerges out of something that wasn't there before. So poetry can be considered a kind of poesis, and I think that programming also represents poesis. And that poets and programmers, because their work is poesis, this kind of making, can help us understand usefully some quite deep questions about ourselves, and particularly about the nature of our human consciousness, our thought, or the mind. So let's go straight into the work of programmers and artists. Programmers seem to be particularly fascinated by rule-governed play when they find it, and they respond to it strongly, especially in poetry and art, for example. And there are some poets and artists and writers whose work and ideas speak very strongly to programmers because of this. And I think that there's something in programming, or no, I think there's something in the way that programmers think that make them especially ready to understand and appreciate the intersection of these things, these work and ideas. So there are certain things you know that a programmer is just going to get a certain idea or a certain work or something like that. I think part of the answer is that rule-governed play takes place in systems, which of course programmers are also very fascinated by. And three of the things that programmers love best in systems are interesting outside programming: loops, self-reference, and hierarchies. And these are also the things that make rule-governed play very interesting. And of course, they're also some of the most basic structures and concepts in programming itself, ones that determine the way programming works. So let's start with loops. Even the simplest loop represents power. It doesn't matter how trivial it is, you can still unleash something infinite, and the computer will try to realize it. So there are many constructs in computing. This is kind of the most basic, but also the most beautiful and powerful. I love loops, all of them. But still, the fascination of Go to 10 is quite limited. The only thing interesting about that particular loop is that it's infinite, not because of anything that comes out of it. So that's not very interesting, but when we apply loops to other things, then they get more intriguing. Does anybody know or remember the website textarc.org? I used to spend a lot of time there 15 years or so ago. What it does, it loops over a text and represents it visually, and I can't show it to you on a real website because it's so old that it's Java, and I have to load a virtual machine running Internet Explorer to do that, so I'll just have to show it. This is the text of Alice's Adventures in Wonderland, okay, right round the edge, and then the words in the middle are in their place depending on where and how many times they appear around the end. So look, here's the word, and therefore the character Alice in relation to the entire text, or in relation to the story. Alice is literally at the center of the story of Alice's Adventures in Wonderland. Here's the griffin. As you can see, a peripheral character. Here's a linear sequence through the actual text in TextArc. Go and find TextArc. It's wonderful if you can get it working on your machine. If you can find it working on a MacBook, on a Macintosh, tell me how, because I'd love to get it working again. So in TextArc, we no longer have a sense of the content of the work, but instead we get its structure exposed by a loop presented as metadata. And structure and metadata matter. We've lost something, the content, but we've gained something else because it lets us see new meaning that perhaps was previously obscured. In the loop of TextArc, we can see who is associated with whom or what. We can see who appears when and with whom. We can see who dominates the story. And when I say see, we literally, visually can see it. So don't be distracted that, TextArc is amusing and literary. What it does is powerful and significant, a fact that's not lost on large corporations and governments who understand the power of this stuff too. Google and Facebook know all about structure and metadata. And right now in various countries, governments are anxious to have legislation enacted that will help them look more closely at metadata. Of course, they never do anything like eavesdrop on their citizens, because that would be wrong. They just want to know, some of the metadata surrounding those conversations. So I don't know if you can see that from up there. So storing metadata is not an invasion of privacy. It's a tool that keeps America safe. No one is listening to your calls. So, Congressman, I see here last Friday you talked to your wife, then immediately called an escort service, then a hotel. Of course, we don't know the content of those calls. So, that's your wife now. So this stuff is powerful. Microsoft, I came across this by chance. We use the cloud to visualize information so we can track down the criminals. Yeah, I bet you do. So, on TextArt, the first text you get is Hamlet. It's not there by coincidence. Programmers and people who are doing stuff with language always go for Hamlet. Alice. Or Hamlet. These are the two texts they always go for. There's something special about these two texts. Here's Hamlet. And here's Ulises Carrion. He was a Mexican artist. And I'm going to play you a part of his Hamlet for two voices. So I've got to bend this down, and we don't have direct audio, so I'll just do this here.
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Horatio,
Marcelos,
Francisco,
Marcelos,
Francisco,
Marcelos.
Bernardo.
Okay, so I think this is hilarious. I think this is very funny. But I also think it's not just funny. It's a new interpretation of Hamlet. It's a Hamlet for two voices, left and right. It's the whole of Hamlet. It lasts about 15 minutes like that. Without any content whatsoever. All we have is the structure. So what have we lost? And what are we left with? Well, it's true that you won't know from this that Hamlet is about revenge or murder or desire, and you won't know that Hamlet's a prince or the story's set in Denmark. But there's still a lot to learn. We know who's there at the beginning. We know who's there at the end, which is, if you're there at the end in a Shakespeare tragedy, then that's a big deal. Not everybody gets to be at the end. We can discover whom the story revolves around, who dominates the conversations, who hangs around with who answers whom. So we've lost something. We've deliberately thrown some information away, but we've exposed perhaps some previously hidden information at the same time. Now, when I play this to other people, everyone at first says, what is this? And then it divides the world up into programmers and non-programmers. Because non-programmers say, what's the point? And they're baffled or even irritated, and I've had people really annoyed by that. But programmers love it. Now, you may all be programmers. If you didn't love that, then maybe you just don't have the soul of a programmer. Yeah? So, because also some people who are not programmers love that. So maybe there are non-programmers who have the soul of programmers. But anyway, the point is that programmers get this kind of thing. They understand loops, they understand what's important about metadata, and they know how to recognize a key value pair when they see one. So, you show me some key value pairs, and, well, I'll show you some code, actually. So let me quickly jump into here. So I've got a little program, a little Python program, okay? And it just jumps onto the internet. It uses Beautiful Soup. This is a very useful library for exploring structured text like HTML. It loops through the text, drags things out in pairs, and then passes them to the say command. So I'm going to, this is my little tribute to Ulises Carrion. So,
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Bernardo,
Francisco,
Horatio,
Marcellus,
so,
Francisco,
Marcellus.
Okay, thank you. I think that's enough of that. Okay. So, computers are perfect tools for this kind of thing, for the exploration, the analysis, discovery of texts and language. And if you're interested in doing that, it's very easy and accessible stuff to do. What could you discover with a simple program, like TextArc or something like this? Could you extract the punctuation from a text, maybe, and recognize the author by the punctuation or by the white space? I spent a lot of time with a Raspberry Pi and a little LED, an array of LEDs, visualizing the characters in Hamlet as kind of spiraling outward different colored lights. So it's fun to do, even if you're a lousy programmer like me. There's a massive amount of this stuff going on in the world of literature. There's a whole field of experimental literature that analyzes texts, synthesizes them, deconstructs them. There's the Oulipo, the Ouvroir de Littérature Potentiel, the workshop of potential literature, French, mostly French writers, mathematicians, and artists. I don't really have time to talk too much about that, but I recommend having a look at that. And you don't have to go to experimental literature. Here are a couple of pages from Douglas Copeland's Microsurfs, the vowels on one page and the consonants on the other. And we can play endless games, fun games, illuminating games with text like this. And I'm talking about games and playing, and some of it's fun, but it's also serious, because play doesn't just refer to having fun. Play means the looseness in a mechanical connection. You say it has a lot of play in this connection when the connection's not tight, to the extent to which one side of a connection is free and undetermined by the other. And play is only possible where you have a linkage, where you have a connection, a constraint. If there were no constraint at all, then there would be nothing. You wouldn't have any play, you'd just have no connection. And on the other hand, if the connection was so tight that it were locked solid, there would be no play either. So you only find it where there's a connection and where the joints permit some movement. And the rules and connections in language are just open and enough, and open and loose enough for both rigorous meaning and play within the same system, which is quite remarkable. And this kind of play is something that's enjoyed and exploited by artists and writers and programmers. So we've seen some examples of looping in TextArc and Hamlet, but this kind of play becomes even more interesting when the looping becomes self-referential. So here's Ulises Carrion, again with his first Spanish lesson. I know some of you already know Spanish, but let me play you his first Spanish lesson. So this is Finnish.
Español. Español. Es español. ¿Es español? Sí, es español. ¿Es ese español? Sí, ese es español. ¿Es ese español español? Sí, ese español es español. ¿Es ese es español español? Sí, ese es español es español. ¿Es si es español español? Sí, si es español es español. ¿Es si es español español? Sí, si es español es español. ¿Es si es español? No, si ese no es español. ¿Es ese no es español español? Sí, ese no.
Okay, so this is language about language. This is language looping over its own structures, recursing on itself. It's language eating language. And now, again, I play this to people, and I watch people get angry and angrier as this goes on. Definitely not people with the souls of programmers. And I had one person turn on me after a few minutes and say, "This is a shit way to learn Spanish." So, I love this. Look up Ulises Carrion, bless him. He died young. This is so fascinating. Now, usually when something consumes itself in this way, it reduces itself to nothingness. But in this case, something new, something other seems to be coming out, something new and almost magical, something slightly maddening about it. And it's a perfect example of playing with rules and processes. So as a programmer, it makes you itch a bit. In a way, this is a program that follows its own internal logic, obeys its own rules. And it makes me think, could we make a first Python lesson in the same way? And, we have the technology. We could get Python to consume itself and regenerate itself like this. But I got distracted by my Raspberry Pi and the colored LEDs, and so I never really got much further than that. But, maybe somebody's a better programmer and less easily distracted could come and talk to me about that. So it's a kind of impossible magic when you make something eat itself, but it's a very old, a very ancient concept. So here's the Ouroboros, the snake that eats its own tail, and it's very important. It visits chemists in their dreams, as you'll know if you've studied chemistry. So Auguste Kekules had a dream of the snake eating its tail and provided him with the solution to the puzzle of the benzene molecule after many years of studying carbon-carbon bonding. And it's an ancient symbol of renewal and regeneration in many cultures. And programmers, as much as artists, are fascinated by what happens when a self-reflecting process loops. And as programmers, we're particularly lucky because we've got the perfect tools with which to explore it. And I mentioned magic, you know, it's a kind of impossible magic, but the magic is not just that the snake bites its own tail, because, you know, any idiot dog can bite its own tail and not produce anything magical. The magic lies when something eats itself and then somehow sustains itself, and then something new emerges, something that wasn't there before. And I think it happens in Ulises Carrión. Something new comes out of the loop that wasn't in it when we started, a new thing altogether. And this is the poesis that we're in search of, or maybe I'm in search of. Here's another representation of the Ouroboros, this time by the artist M.C. Escher, who's also fascinated by loops and self-reference. It's a woodblock print with some very interesting things going on. Where does this loop begin? It's a loop. Well, is it one loop or is it several loops? Was there 4 bands going on? So maybe, is that 5 loops? Is it 4 loops? Is it 1 loop? It's looping on different levels. You have to choose the level at which you see it looping. You have to make a decision to hold in your mind when you look at it. There's a hierarchy of looping going on. And this is where things get really interesting. Here's Douglas Hofstadter. I think he's possibly one of the most interesting thinkers you could ever hope to read a book by. He's interested in hierarchies, in multiple tangled hierarchies of self-referential loops. His best-known book is Gödel, Escher, Bach, which explores art, music, logic, and consciousness. And it's an utterly remarkable book driven by this fascination with loops and self-reflecting processes. And he's in search of the ultimate in self-reflection, which is our own human self-consciousness, subjectivity itself. And the book itself loops and recurses and reflects itself at different levels in its own structure. And he's interested in what could emerge from this kind of process. It's a book whose humor and sense of aesthetics will appeal very naturally to programmers. Here's Hofstadter's Law. It always takes longer than you expect, even when you take into account Hofstadter's Law. Yeah, I see, programmers love this kind of stuff. So, we've talked about emergence, where something new and unexpected comes out of a process at some other level. Hofstadter is interested in these emergent properties of systems. An emergent property is one that arises in a system but can't be found in its components. So sometimes the property might be geometrical order. These are rocks in a river where water erosion has produced this remarkable effect. You know, the rocks aren't shaped like that because of some structure of the rocks. There's nothing in the rocks that represents that structure. That's only an interaction between the rocks and the water doing something to the rocks, and the rocks in turn doing something to the water. So the rocks themselves don't have that structure at all. Another example might be an ant column, where column organization is nowhere to be found in the behavior of individual ants. You know, you don't see ants doing that. You can't predict it, and yet a column, a new system, emerges that didn't exist before. Or in art, in the work of Bridget Riley, where the procedure of she follows a line down a page, and it produces through the natural free play of this activity something that's not in any of its components. Or Google's Deep Dream, that uses iterated pattern searching and generation algorithms and matches parts to wholes and crosses levels of hierarchy, and new levels of significance emerge. Or evolution, natural selection in nature itself can be considered an emergent property, something that comes out of basic chemical or biological processes. And there are multiple levels of hierarchy in these systems. Other properties in nature themselves are the emergent features of evolution. So this property that came out in turn feeds back into the system. So there are numerous behaviors in nature whose explanations have been sought in emergence, like cooperative behavior, which is hard to explain sometimes. Why is there cooperation within or even between species when it would seem that at the level of individuals there's no such benefit? So this graph is from a Python library, Axelrod, and it shows the successes over time of different strategies in a tournament of the iterated prisoner's dilemma, which was set up as a search for the secret of cooperation in evolution, first by Robert Axelrod, who was a political scientist in the 1980s. In the first tournament, selfish strategies did poorly. You know the prisoner, I don't have time to explain the prisoner's dilemma, but I think probably most programmers are aware. Look up the prisoner's dilemma. Selfish strategies did poorly. And last year, my friend Vincent Knight at Cardiff University implemented this as a Python library. You can play, you can develop your own strategy and put it into the tournament. It's been wildly successful and has reignited interest in Axelrod and the prisoner's dilemma. Very interesting. So have a look at Axelrod. So those are all examples of emergent properties of different kinds. Not all of them have anything to do with consciousness, of course. But Hofstadter argues that consciousness, intelligence, is an emergent property that arises from systems in the brain. And we discussed loops, first of all, and the magic that seems to follow when loops become self-referential and something new springs out of them. And then Hofstadter is also interested in hierarchy, so that we have loops within loops and loops at different levels in the system. And his thesis is that hierarchies of self-reflecting or self-similar loops that repeat themselves at different levels lie at the heart of cognition and consciousness. That the brain's neurological processes are themselves based on loops and self-reference and logic and play that I mentioned. Consciousness, he says, is an emergent property. It doesn't exist in the neurons of the brain. You know, if you're intelligent, it's not because you have really intelligent neurons. Yeah? You won't find intelligence or consciousness by looking into the brain and looking more closely at its neurons. If we're going to find something there, it will be by studying the system, what happens in and to and between its loops. So this, here we are. We've got this is the impossible magic where something emerges, reflects on itself, feeds back into itself, crossing these levels of hierarchy. Hofstadter thinks that, or argues that this is the origin of consciousness, that self-referring hierarchies of loops lie at the secret of thinking, of cognition. In these merely physical processes in which absolutely no consciousness resides because they're merely physical processes, consciousness belongs at a different dimension. So could consciousness be a system that nourishes itself like the snake eating its tail? Apparently impossibly. And Hofstadter thinks so. In fact, one of his later books is called I Am a Strange Loop, and the I of our consciousness of subjectivity is this process of looping and self-referring across hierarchies. So now we're talking about intelligence and programming in a very different way from the one that followed Turing. We're talking in ways that I think do make it possible to ask meaningful questions about whether machines could think. And it raises the possibility of an approach into cognition research and artificial intelligence that's quite unlike some of the ones we see at the moment that are premised maybe on big data and huge ontologies and brute force is unkind, but I'm an unkind person, you know, on vast computing power. And instead, we begin with the simplest of things, like the simplest concepts and tools that we as programmers enjoy playing with. Play itself, we enjoy playing with play, with rules, with poesis, with analogy making, with processes. So this approach comes into the question of consciousness, of intelligence, as poesis, as a process that is at the same time transformative, that brings forth something new out of the world or into the world. And I think it's very intellectually compelling. And I think at the same time, however philosophically profound it might be, the opportunities for exploring it are right at the hand of even the most novice Python programmer, which is also a fascinating thing. And it gives us a way into this quest that seems very rich and valuable and illuminating and rich for exploration, especially by us, by programmers. But it's more than that, because I think it does something even more important. It gives us a way to look for not just an insight into artificial intelligence, but just into intelligence itself. And I think the kind of post-Turing way of doing this doesn't give us any of those insights. You know, I don't think that Microsoft, you know, Mike Tay, the Microsoft Hitler-loving sex maniac chatbot on Twitter, that I don't think that tells us anything about the nature of intelligence, however clever it might be. And the question of whether Hofstadter in the end is right or wrong, I don't think is that important. It doesn't matter whether he's on the right track about the nature of consciousness and cognition. His ideas are so beautiful and powerful and compelling that we should wrestle with them anyway, I think. Certainly more elegant than Tay or Siri or all these other things that people are doing very clever things with. And my background's not in programming, but in philosophy. I've been wrestling with Hofstadter and these ideas for 25 years, so a long time. And it's really wonderful. It delights me that I'm able to be in the company of programmers who find this stuff because they've got the right souls. They find this stuff so fascinating immediately, and are also fascinated by the poets and writers and artists that fascinate me. And these things that I found in programming, in a way, it's come back in a circle for me, because it's another pleasing circle of something going back to the beginning, these philosophical questions that have been with me for decades. So it's like the snake eating its tail again. There are some references for you if you want to follow up any of these things. I've got my Douglas Hofstadter in that bag. It's just falling apart. It's been with me for a long time, and I'm very grateful to Douglas Hofstadter. So I haven't really taken you anywhere, but I hope I've given you something to think about, and I hope that somebody will come up to me who's a better programmer and give me some better code that I can maybe develop this talk into something that does a bit more Python and a little less talking. So thank you very much. I think we've got time for a few questions, have we? Yeah, thank you. So, I should say, a colleague of mine wasn't able to come, so I'm doing another talk, in case you didn't get sick of hearing me already, on Thursday on documentation-driven development. So, please, if you've got any questions, I'm happy to talk to you now or later.
All right, let's go. Let's go here.
So I heard some critique of like this sort of big data approach to building intelligent systems, and perhaps you can say that you cannot really call them fully intelligent at the moment. But imagine they succeeded and they made like a talking and thinking robot that you can have a conversation with. I guess you would still say that it's just a simulation of intelligence. So I wonder, in your view, what is the difference between a real intelligence and a simulated intelligence?
Well, if Hofstadter is right, we could have an artificial intelligence. And I'm not sure that he is right, but I'd be much more prepared to admit of a Hofstadter-like artificial intelligence than one that is based on, this, as you say, the brute force, big data mining and machine learning, because I don't think a simulation is good enough. Something that's artificial is different from something that's a simulation. Just because something is artificial doesn't mean it's not real. Yeah, it just means that it's been made. So we could have a real intelligence that's artificial, but a real intelligence that's simulated. It sounds like a contradiction in terms if it's merely a simulation, however good it gets. Because what's going on I think the question of what's going on inside actually does matter. Did that answer your question, or?
I think not quite. No. If it's intelligent for all practical purposes, why do I care how it's made inside? I mean, it's intelligent.
Yeah, well, this is Turing's argument. It just seems unsatisfactory to me. We do care what's inside.
Are there any questions? Yeah.
One could take even a more recursive point of view about that question. That is, we saw the Spanish lesson. The Spanish lesson basically points to the idea of an infinite string of Spanish. You get what I mean. The thing is that you get that concept exists linguistically, still is infinite. Is like the fixed point of an infinite sequence. So through language, we can even represent that sort of thing. Fixed points of infinite sequences. That sort of thing sometimes don't exist. So we have signifiers without signified. And the thing is that intelligence itself may be something without a signified.
Also, the first Spanish lesson, I'm afraid, is a bit of a trick, because it's not just folding entirely by itself. There's actually the director, the artist, who makes it go in the right directions. It's not simply putting Es Español at the beginning of everything. It's choosing the right things, and it's playing with them. For example, the fact that some things are homophones in that, the same sounds can be rendered differently, so it can keep asking the question. So it would actually be less interesting if it weren't directed. So there is some energy going into that system from outside. And that, I think, is, if there's something wrong with Hofstadter, that's probably where it lies. Eddie?
Okay, yeah, we got time for one more question.
Hello, and good talk. Do you think that maybe neural nets combine the two approaches to artificial intelligence, as in neural nets have maybe this emergent feature to them, which might be described as emergent conscience?
Yes, I mean, that seems to be very promising and interesting, because one of the things that we've learned from neural networks is that they sometimes do unexpected things. And not just unexpected things that it was left instead of right, but new orders of things sometimes, where a neural network will have an answer or have a response that seems to have stepped out and be looking at the thing from a different level. So that might be a very, I don't know enough about neural networks actually to say anything that useful, but what I've understood is that actually that is a promising possibility. That is the kind of thing. I think that might just be the start of the kind of thing, and then we'll find more surprising things still.
I'm sure we can take more questions offline, but I have to cut you off here.
Okay.
Thank you
Well, thank you
again.
very much.